Hello students, in this video we'll discuss Cesaro Summability. We'll be given a sequence of numbers, given a sequence, A0, A1, A2, AN, forever. Consider the partial sums. Let Sj be A0 all the way up to Aj, the partial sums. And then what I'm going to do is I'm going to define a new type of partial sum. I'm going to define the Cesaro sums. Define Cesaro sums. And what are these things over here? So the Cesaro sums are sigma j. And what those are, they're going to be S0 all the way up to Sj. So you add up the first j plus 1 partial sums, and you divide by j plus 1. Those are called the Cesaro sums. Okay? And so, of course, what are these Cesaro sums? Let's think about them carefully over here. Let's do a little example. And so the example we're going to do is the following. So let's look at these terms over here. So what would, if j was equal to 0, we would just have what? We just have S0 over 1, which would just be A0. So sigma 0 would just be A0, like S0 is. That's great. But let's, for example, look at, for just to get our feet wet, example, I looked at sigma 3. What that will be is that's going to be S0 plus S1 plus S2 plus S3 over 4, right? So how many A0s do I have? This is going to have an A0, this has an A0, this has an A0, this has an A0. So I have 4 A0s, so I'm just going to have A0. But then how many A1s am I going to have? This will have an A1, this will have an A1, and this will have an A1. The next three have an A1, so I get 3/4 of A1. Plus how many A2s? I'm going to have 2/4 of A2. Plus 1/4 of A3. So it's linearly decreasing the weight on the numbers Aj the deeper you go in the series. So you can show actually that what's going to happen over here is that notice we start and then we get to the very last one with a 1 over j plus 1. So that of course corresponds to my 1 plus 3. And so what we're going to have over here is we can see that these Cesaro means are really just the sum. J goes from, well, I have j over here, so we have to use a different index now. So let's use a different index. Let's say these sigma j's are going to be k goes from 0 up to j, and then 1 minus j, k rather, again, I'm used to my different notation, so k over here, k over what? We'll have to figure that out. It's going to be an ak. So when k is equal to, so of course we need to get 3 over 4, so over here, so that corresponds to 1 more than that. So I need to have when k is equal to 1, I need to have a total of j plus 1 over here. So the j, so this is my j over here, and the denominators are all 4s. So I need to have all 4s in my denominator, so I need to have a j plus 1 over here. Let's see if this works over here. When k is equal to 0, I just get A0. When k is equal to 1, I'm going to get 1 minus 1 over j plus 1. So that's going to be a j over j plus 1, which is exactly what we have over here, j over j plus 1 A1. So this is the formula how it works. So in other words, I have a linear weighting decrease. So I'm weighting, these are weights on my sequence over here. So that's what these Cesaro means look like. And so what I'd like to show is the following. So there's a proposition. So the proposition is the following. Proposition. Suppose that these Sj converge to S. Then the Cesaro means also converge to S. Okay? And so here's the idea. So the idea is that since Sj converges to S, we can pick, here's the proof, pick n in n such that if n is bigger than or equal to n capital, we have the absolute value of Sj minus S, whoops, I'll say Sn minus Sn minus S less than epsilon whenever this is true, right? So I can certainly make that happen. Now my goal is to show that sigma, for this same value of n over here, which is fixed, that sigma n minus S is less than epsilon, okay? So let's do the following. So let's look at sigma n minus S. So now sigma n minus S is what? So sigma n minus S is going to be, well, sigma n is going to be S0 plus all the way down to, let's assume that, of course, that n is bigger than or equal to n. We're going to assume in that same regime. I'll go all the way up to Sn minus 1 plus Sn all the way down to S little n, all divided by what? all divided by, now this is going to be my j is equal to n here, so I'm going to have an n plus 1 in the denominator, okay? Now what can I do? I can assume, since the Sj converges to S, we know that Sn is less than or equal to m for all n. Okay. Now why is that the case? Any convergent sequence is bounded, so I know that these Sn's are bounded over here. And so now what am I going to say? I'm going to subtract off n plus 1, I'm going to subtract off S from this over here, but really I'm going to subtract off n plus 1 S over n plus 1, right? So let's put absolute value everywhere over here, like that. And now what I'm going to do is I'm going to feed one of these S's to every single term over here. So I'm going to have S0, we'll have an S0, S0 minus S, plus S1 minus S, plus Sn minus 1 minus S, and then plus Sn minus S, all the way down to S little n minus S, and all of this is less than or equal to over n plus 1 over here, okay? Good? And so now what can I say about each of these terms over here? These terms over here are all less than epsilon, and then I'm going to have some function like n minus little n capital, right? So these terms over here, so I'm going to break this into two terms. So I'm going to consider these terms over here. I'm going to consider those terms, I'm going to call those terms 1. And I'm going to call these terms over here, I'm going to call these terms, let's do it in blue. These terms over here, I'm going to call those terms over there too, okay? Now what can I say about 1? 1 is going to be less than or equal to each of these terms. I'm going to put absolute value in each of these terms over here by the triangle inequality. Now Sn minus S, all of those things are less than epsilon for those values of starting at n. So all of those things are going to be less than epsilon. So I'm going to have n minus n, no more than n minus n, epsilons over n plus 1, like that. And then what do 2 look like? The 2 terms are bounded by, the 2 terms are less than or equal to what? Less than or equal to, well, all of these things are bounded by m, so there's going to be an m, 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 all these m's. So how many m's do I have? I have n m's, so n m's. There's probably a plus 1 over here too. I can make this a little bigger to make sure it's less than or equal to that. I'm going to have n terms over here, n terms over here, times 2, and then m over n plus 1, bearing in mind that n now is fixed and so is m. And so now what can I do? I can take the lim sup of these expressions as n goes to infinity. So if I take the lim sup as n goes to infinity, the lim sup as n goes to infinity of these expressions is less than or equal to the lim sup of these things over here. The lim sup of those things are less than just epsilon in lim sup. And then the lim sup of these things over here are going to 0 in lim sup. Okay? So all total, we've just proven that the lim sup as n goes to infinity of sigma n minus s is less than epsilon for any epsilon, less than or equal to epsilon for any epsilon, and that shows that the sigma n converge. Therefore, sigma n converges to s as n goes to infinity. So our sigma n does converge to s as s goes to infinity, and that's the proof that if you are summable, then you're also Cesaro summable. Thank you very much.